Okay, hi everyone. Welcome to SDS1101, Introduction to NLP. So this is a non-credit bearing workshop conducted by the NUS Statistics and Data Science Society. Okay, can you all hear me?
Yes.
Can. Okay. Okay, so if you all have any questions throughout the presentation, you can head to the Slido website, and then this is the code for the Q&A. So I'll just paste it in the chat. Okay, so let me carry on. Okay, so these are our team members for today's workshop. So there's me, Stefan, Javier, and Edmund.
Wait, you may want to turn off the music.
I'm not playing
You may
music.
want to turn off the music.
What music?
The music.
Wait, there's no music, right?
Oh, my bad. That's me.
Okay. All right, so these are the workshop goals. So the workshop will be held in two parts, today and on Wednesday. So throughout this workshop series, we would like you to, first of all, understand fundamental ideas and concepts in NLP, have an awareness of common NLP libraries and what they can do, and finally, be able to apply all that you've learned about theory and code to execute a basic NLP project on Kaggle. So we're going to be doing sentiment analysis. Yep. Okay, so here's an overview of the workshop series content. So for today's workshop, we'll be doing introduction to NLP, basic pre-processing and feature engineering of textual data using the NLTK library, and the naive Bayes model, which we'll be explaining the theory for first before applying it to do sentiment analysis. Then as for this Wednesday's workshop on applied NLP, we'll be doing NLP related to deep learning, so neural nets, recurrent neural networks, LSTMs, as well as attention and transformer models. So these are some of the more cutting edge techniques being used today. Yep. Okay, so now I'll go over the introduction. So to give everyone a brief overview of NLP. Okay, but before I start, let's do a live demonstration first. So this is the Open GPT-3 language prediction model. So it's a fairly recent model that was released in 2020, and it has a huge amount of parameters, 175 billion. So it's a really massive and a rather interesting model actually. So we're going to try out some prompts to see what happens. So as you can see from the screenshot, here's a prompt that I put in at first. So I typed in hello. Today I'll be introducing NLP to all of you, firstly, comma. Then after that, I just hit the generate button. Then it came out with all this text. And if you read the text, right, it actually looks pretty legit. Okay, so it's really cool. So today I'm gonna let all of you suggest prompts that I can give to OpenGPT-3, and we're gonna do it right now. Okay, so feel free to just type the prompts in the chat, and maybe I'll choose around 3 or so. Yeah. Okay, anyone just type your prompt in the chat, then I will submit it to OpenGPT-3. Anyone? Okay, maybe I'll start you off with a prompt that I prepared. Oh, okay. So someone said, what can we do during recess week? Let's try. Okay. So here's the text that it generated. So you can see it's quite legit, right? It's actually a coherent sentence, and the answers make sense, I guess, in the context of it not knowing that it's an academic research group. Yeah. Okay. So someone else asked, why are NFTs? So it's why, right? Not what, right? Okay, let's try. Okay, it's basically answering the what question. So yeah. Then another thing you can do is you can adjust some of the parameters. So this one adjusts how random the generated text is, and then this one shows the probability of it choosing certain words instead of others. So I'll show you what I mean. So submit. Yeah, so you can see, right, that because of the randomness factor, it chooses certain words over other words. So there are some alternatives that you can use, like instead of own, it can be exchanged or used. And then it picks them randomly. Yeah. But of course, some have a higher probability than others. Yeah. Which shows that they are more likely to fit in the sentence. Okay, so anyone else got a prompt? I can do one more. Otherwise, I'll just use my own. Yeah, let me use my own. Okay, so maybe I'll give you a story, okay, and get you to complete the story. So once upon a time, there lived an angry boy in a rundown house at the edge of the woods. So one day, the boy, then I just tell it to finish the story. And actually, this prediction, right, is quite random because I did it before the presentation and it gave a different story. Yeah. So now it's giving me a story about bread. Yes. So we can do a lot of interesting things. Yeah. Okay, so that's OpenGPT-3. So let's carry on with the presentation. Right. Okay. So now that you've seen this really cool and exciting NLP product, right? Let's try to understand what NLP is properly. Okay. So first of all, let me explain what natural language means. So natural language is any language that has evolved naturally in humans through use and repetition without any conscious planning. So for example, speech or written text would be considered under natural language, while something like formal mathematical notation or a coding language like Python or Java would not be considered natural language because those are constructed artificially and deliberately. Yeah. So then what is NLP? So NLP is a very broad field, but it can be described as the application of computational techniques to process, analyze, and synthesize natural language. So tasks that would fall under the purview of NLP would include things like translation, question answering, and speech recognition. So there are different levels of NLP applications, which I will go over on the next slide. Yeah. So when we do NLP, we can operate on many different levels, and it's possible to distinguish them using the following framework. So these levels start from smaller components of words and gradually build up all the way to sentence structure and even incorporating real-world knowledge, which you can see here on number 6, which is pragmatic analysis. So this part is pretty theoretical, so don't worry about the specific levels for now. I think more importantly, just note that there are different levels and an NLP system might end up using multiple levels depending on the application and implementation. So a simpler one might only use like morphological analysis, for instance, but the more complex NLP system like a translation one would need something like semantic analysis because it needs to understand the meaning of sentences before being able to translate them. Okay, so what makes NLP a challenging field to work with? So there are many difficulties, but they mainly revolve around the problem of having to teach a machine to understand all the complexities and subtleties of human language. So for instance, how will you build up a representation of a sentence or paragraph or an essay in a computer format? And also, you can think about how one would represent all the rules that are involved in language for a computer to understand. So how do you even explicitly define the rules, and do you even know what are all the rules? So as an example of how actually defining all the rules of language can be a real challenge, take a look at this paragraph that I took from a book. So it says that adjectives in English absolutely have to be in the following order: opinion, size, age, shape, color, origin, material, purpose, followed by the noun. So you can have a lovely little old rectangular green French silver whittling knife, but if you mess up that word order, you're gonna sound like a maniac. So it's an odd thing that every English speaker uses that list subconsciously, but almost none of us could actually write it out. Yeah. So as an example of how it sounds weird to us when we mess up the order, you don't say green great dragons, right? It sounds odd. You say great green dragons. Yeah. Okay. So maybe you all have heard of the Turing Test. So the Turing Test is a mark of a machine being able to execute intelligent behavior. So in this case, holding a conversation that's indistinguishable from another human. So basically, I get you to converse with a machine, and then you aren't told it's a machine. So your job is to tell me whether you are talking to another human or actually or a computer. So for now, no machines have been able to pass the Turing test convincingly. Yeah. So which goes to show how hard NLP is. Yep. Okay. Okay, so now let's try to take a look at how researchers have tried to tackle the problems in NLP over the years. So as I said earlier, right, we have the Turing test in 1950. So following that, for around 30 to 40 years, symbolic NLP methods were the most popular. So what are symbolic NLP methods? So basically they are rule-based and they follow a complex set of handwritten rules. So for example, to do spell checking, you need a lot of rules to make sure that the paragraph conforms to the correct spelling. Yeah. So this requires a lot of expertise and it's really difficult. And additionally, it won't work with unfamiliar input because then your rule set will not cover that input, right? So, but there are situations where you can use, where symbolic NLP still remains useful. So for example, if you have very limited training data, then maybe you would have to manually define the rules for the model. Yeah. And also when you do manual pre-processing of your input data, you are still following a set of rules, essentially. Okay, so in the 1990s, then statistical NLP methods became very popular. So basically people turned to ML techniques in order to do NLP. So they use models like decision trees, Bayesian networks, and so on. So these statistical techniques allowed people to create robust NLP models that automatically learn and make inferences from data. So you're going to see an example of this later with the naive Bayes model, which makes decisions using probability. Okay. So, and then in recent times, I think everyone is familiar with this nowadays, right? So we have neural networks, right? So similarly, deep learning has revolutionized the NLP field as well. What with all the big data, faster GPUs, and advancements in model architectures. So nowadays, cutting edge results are mostly obtained using the neural NLP models. So we are going to cover some of these in the second workshop. Okay. So, all right. So now I'm going to go over some applications of NLP. So on this slide right here, I have a text summarization model. So basically what it's doing is that it's taking in an input article. So in this case, it was a news article from CNN. And then it's basically summarized it into a single sentence. So what it generated here was that according to the prosecutor, no videos were used in the crash investigation. So to the model, the text summarization model, this is the sentence that sums up what the whole article is trying to say. And then there's also a more comprehensive summary that it comes up with. So you can see it's still a bit rough around the edges. Like you see the punctuation is a bit weird. Yeah. Okay. So what else can NLP do? NLP can also do sentiment analysis. So this is the thing we're going to be trying out later with our own models. So basically what sentiment analysis is that it takes in a sentence or a chunk of text and then it tells you whether it has positive or negative sentiment. So for example, let's say, see, a bright and sunny day, spring at last. So it classifies this as positive sentiment. And then this guy is complaining about his laptop. So that's negative sentiment. Yeah. Okay. So what else? I think this one everyone is familiar with. So Google Translate. So that relies on complex NLP models as well. And I guess if you have been using it for a while now, right, you might have realized that it seems that these models are getting better and better. So in the past, Google Translate was not that good, but I feel like in recent times, it's gotten a lot more accurate. Okay. And then maybe this one you've probably encountered in your school email, the auto completion or text suggestions. So basically what's happening here is that the NLP model is trying to predict what text you're going to type in next. So ideally this would help you to draft your emails faster. Yeah. Okay. All right, and maybe another example of such a thing would be something like Grammarly, right? So Grammarly helps you to fix your sentence structure, rephrase what you're writing. So something like that will also rely a lot on NLP models, because the model has to understand, first of all, what you're trying to say before it can rephrase it in a more grammatically correct manner, or more concise manner. Yeah. All right. Okay, then here's the final application of NLP. So this was a screen grab from the chatbot on the MOH website, Ask Jamie. So it was actually taken down for a period of time because some users discovered that it would give like amusingly wrong answers when given certain inputs. So you see here, they typed in a sentence about testing COVID-19 positive, and then what should I do? And then here you see Jamie giving a totally nonsensical answer. Yeah. So so this is just a reminder that AI solutions are not infallible, right? Many exhibit biases as a result of the data they are trained on. So your data could be incomplete, it could be non-representative of the real world and so on. So we should always remember to take all these into account when creating AI solutions. Okay. So next, I'll go over the general workflow for doing NLP. So you see this part, I tried to ask OpenGPT-3, and then it actually gave a pretty legit series of steps. So you say choose the right algorithm, pre-process the data. So yes, but unfortunately, I can't get the model to teach the whole workshop. Yeah. Okay, but so what should we do when we want to solve an NLP problem? So the first and foremost, we should do exploratory data analysis. So that's EDA. So for example, something like doing word clouds to visualize what words the input contains the most. So this helps us to understand the data set and form our own hypotheses before actually creating models. So it's important that we carry this out. Okay. So after you've done EDA, then you can do data pre-processing, because at the start, what we have is very raw input data. So we should generally try to convert this into a more useful and understandable form for our machine learning models. Okay, so steps involved in data pre-processing include things like tokenization and removing stop words. So Javier will be going over all these pre-processing steps of data, but for example, just as an example, removing stop words basically means I take away words that are known to not really mean much in my input. So for example, stop words could include things like the, is, are, and so on, right? So I take this out to reduce the amount of noise in my input data, okay? But just as a word of warning, which pre-processing methods to use is debatable, right? So there is debate over like whether, for example, you should remove stop words at all, or which words fall under stop words. Like for example, would the word not be a stop word? So I think by default it is, but not everyone will agree, because for example, saying something is not easy versus saying something is easy, right, is totally two different things. So something that we need to think about when doing data pre-processing. It's not just blindly applying every pre-processing step you can think of. Okay. All right. Okay, then following pre-processing, then what we can do is feature engineering. So this is when we try to create more useful features out of our input data. So for example, stuff like parts of speech tagging, TF-IDF, and so on. So again, we are going to be doing this later, so I'm not going to explain. But just as another note, feature engineering is not as important for deep learning methods, because what deep learning methods basically do is something called automatic feature extraction. So basically the model learns how to extract the most useful features from the data in order to make the predictions. Okay, so the feature engineering is more useful for traditional ML models. Okay, so following feature engineering, then we can do our model training, followed by model evaluation. So for model evaluation, what we need is a quantifiable performance metric. And this is not always easy, especially in an NLP context. So for instance, like how will you compare two translation models, for example? Like how do you say that, oh, this model is better at doing translation than the other model? So it's not that easy to say for sure. Yeah. So assuming we do our error analysis, then after that, that allows us to make changes to our model or even to our data set. And then following that, we run through the entire pipeline again. Okay, so doing NLP and data science in general is a very iterative process. Okay, we train our model, we evaluate our model, then we try to make changes to improve our model predictions. Okay, so that's it for the introduction. So now I'm going to pass the time on to Javier to do text preprocessing using the NLTK library. Okay, right.
Okay, hello. You all can hear me, right?
Yeah, can.
Okay, thanks. Okay, so thank you, William. And let's move on to the more practical part of NLP. So just another reminder that this is not a credit-bearing workshop or module. So don't go and claim any MCs from your prof, okay? Okay, so in the practical part, in my part, I'll just be going through the pre-processing, the how to use NLTK, and yeah, and how to use NLTK. And afterwards, we'll have Edmund who will go through how to build our very own naive-based classifier. Okay, so as usual for most data science stuff, let's use pandas. So we import pandas, and then we can use this curl function, which actually just downloads the data set from online, from some GitHub repo. And for today, we'll be using the Imdb data set, which is a very popular data set, which is, we can see it's a very simple data set. It's just consisting of a lot of movie reviews and the associated sentiment. So note that we have 50,000 reviews here. And this is a labeled data set, which means that each review has been labeled by a person, that whether it's actually positive or negative. Okay, so since this data is so clean today, we can skip the cleaning, and since we don't have enough time, we also are going to skip the exploratory part of it, and we'll jump straight into pre-processing. Okay, so for my part, we'll just be using the very first example of the review to go through all the different steps and things that you can do. So we can see that this review, right, we just have to read the first two sentences. One of the other reviewers has mentioned, after watching just one Oz episode, you'll be hooked. They are right, and this is exactly what happened with me. So for us, right, because we are humans and then we are quite used to this, it's very obvious that this is like a positive review, right? But a computer cannot understand that it is positive or negative just like that. So we have to help it a little. At least they cannot understand like right now. I mean, next time if we have like the super AI or sentient AI, then maybe they could. But for now, we need to help it a little. So let's just start by changing all the words to lowercase. Okay, so we can standardize everything. And we just use the Python's string libraries function called .lower. And we see, okay, now we have this. Now, if we look through, right, we see there's very weird stuff like this BR text over here. So if you don't know, this is actually some HTML tag, which stands for break line, which is essentially just an empty blank line. Okay, so how do we remove them? There are a few ways we can do it, and I think one of the so-called easier ways we can do is make use of a library that we already have. It's called Beautiful Soup. Yeah, really cool name, right? and we just import beautiful soup, and then we create this function here. So what it does is take a chunk of text and create a beautiful soup object using a HTML parser. So it looks at this whole text as HTML. So it will recognize that this BR tag is not actually part of the text. And then we get the text part of it out. And we can see that, look, now it's gone. Okay, it's gone. Okay, now the next thing we can do is expand contractions. So contractions are basically words, like, because we are too lazy, so we combine words together, right? So stuff like here you have you, which is like you will, and we have I can't do this, is I cannot do this. But so why do we need to expand contractions? That's because, let's say if we don't, there may be a chance that when we split them up into individual words, that some details will be lost. So it might become I can do this. So of course this is very positive thinking, right? But that is not the actual meaning that we want. So what we can do is we use this library called Contractions. And basically this contraction library is just a very, very huge dictionary which contains all the contractions and as a key, and then the value is the actual 2 words or 3 words that are together. So we import contractions, and we can just look at the contraction dictionary and look. So we have like stuff like where's, then and the associated like expanded form. So how do we use this? So in the contractions library, right, there is a method for us. It's called fix. So we just call contractions fix, and we put in the word inside, and we can get the expanded form. Or the other way, since we know this is a dictionary, we can just index it using the key by contractions dictionary, and then index using the key here, and we'll get the same thing. Okay, so now let's look at the example review again, and we notice that we have a few contractions here like you and who, this kind of stuff. So how do we go about changing all of these words? So again, I think a very useful library we can use is the RE library, which stands for regex or regex, regular expressions. So we use this function called sub, which just replaces. Okay, so this is a pattern that we define. This is a regex pattern, and what it means is that you want to find word characters, more than one, and then with an apostrophe followed by more than one word character again. And the second argument is a function. So what this function does is it takes in every match that is specified by us, and then it calls the function that we learned just now, contractions fix, on this match. So what this does is it returns a match object. So we have to call group 0 to take the entire match. And then example review is just the text that we want to use this entire function on. And we just run it, and we see that the you expanded to you will, and stuff like the who expanded to who will. Okay, so now the computer still cannot understand. So what we can do now is something that is called tokenization. So tokenization, there's two main tokenization that we can do, which is word and sentence tokenization. So it's quite intuitive, right? So word is basically just splitting up the entire text into individual words, and then sentence is just sentence. So we are using NLTK for today, but of course there are a lot of, that's like, you can use Spacey or other NLP libraries that you can think of. So for NLTK, we have to download this library called the Punct. So this is from the documentation. Punct sentence tokenizer divides a text into a list of sentences by using an unsupervised algorithm. So what it does is this Punct tokenizer has been trained on a lot of text such that it knows how to split the words up into individual words. And for your info, if you want to, you can actually train your own tokenizer using the Punct sentence tokenizer with the Punct trainer library. So, however, we will not be doing that today because you need a lot of data for that. So it's very simple. We just import the word tokenize and send tokenize from the NLTK tokenize, and then we just put in the review, and we can see that it managed to split up all of the words into, and you notice that it also splits up punctuations here. which might not be very useful for our naive-based model. So we work on that afterwards. And send tokenize is the same thing, very easy. So it returns a list of sentences. Okay. So now let's remove punctuations. There are also a few ways to do it. The first way I can think of, which is quite easy, is using the string library. So if you can import string, and we see that string punctuation returns a string of all the different punctuations we can have. So we just use a simple list comprehension here, which is, this is basically a for loop. So for word in the tokenized words, if this word is not in a string punctuation, which means that it is not punctuation, then we will append the word to the list. And we can see that, yeah, all the punctuations are gone. And then we can do the same thing for the sentences. So we can use the sub function again. So what this means is, this caret here, right, means that not. So you want to match for things that are not alphabets, A to Z, and not numbers, 0 to 9, or not white space, which is this \s. And then it replaces those things that are not with white space. And then we see that the sentence is clean and there is no punctuation anymore. So what can we do with like word or sentence tokenization? So like what Wei Liang said just now, we can use it in our EDA or stuff like that to get a frequency list to see if like a certain word is used a lot or very little, and like how many times it appears on average. So NLTK also has a very convenient library function for us, which is called freq list, which is just frequency distribution. So we just import it and we can just call it like that and pass in the tokens or pass in the text. And then we can call this method called most common. So you can see the most common words are the, is, of, os, and. And another way we can see is using the tabulate, which just prints it out in a table form. Okay, and like what Wei Liang said just now, some words are quite useless, right? Like we can see the. So what if I know that the appears a lot of times in the text? It's not really going to help us in this context, right? When we want to try to predict whether a review is good or not. I'm pretty sure the, is, of, this doesn't even give us much context or much information. So these words are called stop words, which essentially are useless words if you put it. And yeah, so how do we remove this? So NLTK, of course, has a corpus of stop words. So a corpus means, it just means a collection of text. And we can see that, yes, so here are all the stop words which NLTK deems as being like useless or doesn't help much. Of course, it is quite subjective, and maybe you will think that you want to have some words inside, like maybe you think between is actually useful. So actually you can remove the stop words from this one before going on to clean your sentence up. Okay, so how do we do it? Of course, we're going to do it using list comprehension again for all the word in the tokenized words. Like how we did the punctuation. If the word is not in the stop words, then we append the word here. And we can see that, let's compare to the example review. We see one of the other reviewers has mentioned, and we can see that now it becomes one reviewer's mentioned watching one OS episode. So from here, we can see actually the whole meaning is somewhat preserved, right? Like even just reading this, we can somewhat tell that, yeah, it means like one person mentioned this. Yeah. So it helps to reduce the size of the data that we have. Okay, next thing we can do, for example, if let's say I tell you, I went to play yesterday, or I was playing yesterday, or I played yesterday. So as humans again, we can we know that these three actually mean like the same thing, but a computer doesn't know. So because if it's just comparing words, it's obviously going to say that play is different from playing, which is different from play. So it wouldn't know that we actually want to mean the same thing. So there are two main ways that we can do this, which is stemming and lementization. So what is stemming? You can see it as like cutting the plant at the stem. If you want to go and grow a plant, you cut it off at the stem and you can go and root it. So stemming is really literally just cutting off words. And here's the table so you can visualize it easily. The left column is the actual word. The two middle columns are different stemmers, and the last one is a lementizer. So you see the problem of stemmers, right, is quite obvious. it sometimes doesn't return us an actual legit word. So you have like from wrote it becomes wrote. Remembered becomes remember. So it's kind of weird. And we see that Lementizer actually returns us actual words. So there are trade-offs to this. So the main trade-off is that basically stemmers work faster because they just cut off the word there. And Lementizer is slower because you have to take into context. Like it knows that wrote is a past tense of write. And like thinking is like continuous tense of think. So it acts accordingly. So this is a trade-off. If you want a more accurate data, you obviously will go with Lementizer. If you want just quick and easy, fast data, you can go with stemmers. So NLTK has stemmers and Lementizers, and very easy. We just download the word net, and we just import the Lementizer, import the Porter stemmer and the Lancaster stemmer. So it's very easy to use, right? You just create the Lementizer, the Porter stemmer, and the Lancaster stemmer, and then we just call it from the word. So let's just see what are the differences here. So if we look at the first one, right, using Lementizer, we can see that it feels like it hasn't changed much from our original one, but it might be good or may not be good in a sense that most of the meaning is still there. However, if we look at Lancaster stemmer, it looks like it does the worst. From one review mentioned, become on review meant. Yeah. So this looks like it doesn't do very well as stated just now. So we might, but however, Porter stemmer looks like it's still okay. One review mentioned watch one or is. Yeah, so it's really very subjective and it's up to you to decide if you're going to use a Lementizer or stemmer. Okay. So now let's move on to some extra learning because we wouldn't be using this for our naive based model later on. So like what William mentioned just now, first one is part of speech tagging. So what are part of speech? It's basically like what we learned in primary school, like your nouns, adjectives, verbs, adverbs, stuff like that. And then we're just going to tag each word in a sentence to one of these part of speech. So very simple again, we just download the perceptron tagger and we just call NLTK pause tag and pass in the words. And we can see that you have each word, it returns a list of tuples where each word is tagged to a part of speech. So here we can see that 1 is tagged to CD, which is cardinal number. And then like mention is VBD, which is verb past tense. So things like that. Okay. And then what this function does, okay, I'll be just going through very quickly now. This function just basically takes, gets the part of speech for each word and then put it into the Lementizer that we used just now. Because as we saw above, right, the previous Lementizer field felt like it didn't really change much. So this is one way that you can improve the accuracy of a Lementizer by putting in the associated part of speech with each word. And we can see that now it becomes one reviewer mentioned watch, and we see above is mentioned watching. So just now it didn't remove the past tense and the present tense continuous tense. However, once we put in the associated part of speech, it knows that mention is like a verb, so it can probably remove the past tense, and watching is also a verb. So yeah, this is one way to improve the accuracy. Okay, moving on. So next thing we can do is name entity recognition. So what this does is just categorizing each name entity, which are like I'm given here person, organization, location, and tagging, categorizing them. So we'll see here that I have an example sentence, and then first thing we do, tokenize it. Second, get the parts of speech, and third, just put it in the any chunk method. And we can see that data somehow they tag it as an organization, but this national university is also an organization, and Singapore as some geographical thing. So yes, these are things that you can do if you want to improve your models or the accuracy of your models, but we will not be using it today. And then the last another thing that we can do is n-grams. So what are n-grams? Here's just a code. It's a continuous sequence of n items. So bigrams is continuous sequence of 2 words, trigrams is 3, and ngrams is however many you want to specify. So also very easy to implement using NLTK. We just import the bigrams, trigrams, and ngrams, and then we can just put it in. And you see that bigrams pairs up the words into 2s. So one reviewers, then reviewers mention watching. And then we see that trigrams in 3s, and if we use ngrams, we can specify like, let's say 5, and we can do this. So what's ngram for? Ngram is used so that you can get some kind of probability method, or you can take in some context. Like we know that we can look at the words before and after the word that you want. So yes, as mentioned, we will not be using today. We will be using unigrams, which just each word as a token on its own. Okay. Next thing we can, okay, now let's come to the last 2 things. So these are 2 things that are quite essential for our naive Bayes classifier. So first one is called bag of words. What bag of words is literally, you can imagine it as you have a whole bag. You just throw in all your words. So what it does is just count the number of times your word appears in a text. So this one will be using the scikit-learn library. It's called from the feature extraction text, and it's called count vectorizer. So we just create a count vectorizer object, and we transform it using the review that we have. And if you create a table here, we can see that your appears 184 times, you appear 183 times, wouldn't appear 182 times, stuff like that. So what are some limitations of bag of words? So basically, as I said, right, if you have a bag, you throw in all the words, it means that you are messing up the order. You're not taking order into context. So the only thing that you can get out of this is just how many times the word appears. And the thing is, it may take up a lot of memory because you're throwing every single word in and just counting. So if your text is very big, this might lead to some memory problems if you are running your code. And yes, so to combat the context, to combat some of the limitations of that, we have what is called TF-IDF, which is term frequency inverse document frequency. It's a mouthful, but however, what this does is that basically we know that some words appear more often than others, but is that word actually really useful or not? So like stuff like like all those words appear a lot of times, but we know that they're not useful. So what TF-IDF does is it helps to balance out a little. So this is the function. You don't have to be so concerned about it. It's just basically the term frequency, which is the number of times this actual word appears in the document, multiplied by the inverse document frequency. So the inverse document frequency, right, is that you can just see it this way. The less time it appears, the more important it is. Because let's say, for example, you have some very special words, like some special names or terms or scientific names or words, right? But they don't appear as many times as the more common words like the and like all those words. So it's taking an inverse of it. So the less time it appears, it's treating it as more important. So with these 2 calculations, you just times them to get multiply them together, and you get the TF-IDF of this term. And we also can implement this very easily using the scikit-learn library, the feature extraction text, call it TF-IDF vectorizer. So we just create the TF-IDF vectorizer, and then we just feed transform with the text that we have. And creating the table, we can see that yes, although these few words still come out as top, however, it's more balanced out now. And we do note that if you want, you can use your stop words together with this to remove all these other words too. So yes, so these are all all the very common pre-processing things that you can do for your NLP before you actually create your model. So I know it may seem kind of boring, but do note that pre-processing part is the very, very, very important step before for NLP and for any other data science stuff, because if you don't have good data, no matter how good your model is, you will not be able to get a decent output. So yes, so these are things that you can do and how to implement it with NLTK. And now we'll be moving on to the model that we'll be doing today. And I'll pass my time on to Stefan.
Okay, give me a moment. Okay, let's have like a 3-minute or so break. I think y'all have been sitting through very attentively. So y'all can ask some questions, play some corporate music for in the interim, and y'all can like take a toilet break or something like that. Yeah. Are you able to hear the corporate music?
Not really.
Oh, oops. Why use a tokenization? It was by using the tokenizer from Nlp tool. I think generally just makes it like a bit more convenient. I think there are also some extra optimizations. You can use regex.
Sorry, Stephen. We can't really hear you because the music is like covering your voice.
Okay, I guess I'll just answer it here. Yeah, so you can use split. However, if I'm not wrong, NLTK can you can also input with regex. So it has regex built in, so you don't have to do the regex compile and then like add in extra imports and whatnot. Yeah, pre-processing for this data set, it kind of works in general. I think you may need to do a little bit on the regex side as well to kind of clean some of the steps out. But it really depends on what your task is for the data set as well. And for TF-IDF, so word frequency in sentences. So there's actually a quite interesting kind of idea that's going on in TF-IDF, where essentially it's trying to take the inverse, like say, the semantic amount of meaning of the word in accordance with the data set as well as the document itself. So meaning that like words that are used like less frequently and taken out of like stop words are more often or more taken to have more semantic meaning or like impact in terms of how the model would view it. Okay, I think we've answered some questions and we can continue on with the presentation on Bayesian. So let me go to the next one. So naive Bayes. So NLP to Bayes theorem to the naive Bayes. So in order to kind of understand the naive Bayes algorithm.
You haven't shared your screen.
Oh no, I'm not sharing the screen. Oops. I've not been sharing my screen. Oh, oops. So sorry. Yeah. Okay, so naive Bayes. So from NLP to Bayes theorem to naive Bayes. So let's first tackle where we're coming from. So we're coming from like just having processed a bunch of words into a bunch of count vectors. So a little logical link I like to use is Dr. Seuss's Green Eggs and Ham, which is a book that you may or may not have heard from when you're or have read when you're younger. So take this excerpt from the book. So I do not like green eggs and ham, says Sam I am. So we can process this into the set of the tokens in the word, right? So I'm just going to simulate as if we've done it, right? So we've taken out the stop words I and N, and also do and not. I think I didn't update this one, but yeah. So we kind of get if we look at this probabilistically, right? We get an event space and a sequence of events. So what is the event space? The event space is the total set of words in the 50 unique words of Dr. Seuss's Green Eggs and Ham, and a sequence of events, that being this particular sequence of words that we are putting into our event. So it's our event that occurs, or rather it's a chain of different words that occur together in a sequence of events. And so this is a little bit more familiar if you've done some probability classes. If you've not, this is the kind of way they say it. So they call like probabilities like events, I guess. Yeah. So let's jump into a little bit more of the Bayes theorem itself. So what is the motivation for Bayes theorem, and why is it important? So important that we need to cover it, and you should understand it as well. So it is a probabilistic way to update our current belief given new information about a population or total event space. So meaning that when we are calculating or when we are like viewing a certain subsection of events in, let's say, two coin tosses or something, what's the Bayes theorem kind of understanding of it? Or I think a bit more relatable kind of analogy would be, so I drink water and then I choke on water. So the prior belief is that I'm drinking water, right? And then a new evidence is that the water goes into my throat. And then the updated belief is whether I choke on the water or not, whether I'm coughing up water or like I drink a glass of water and I feel refreshed, right? So this is a way to represent that change in subjective view from a prior belief about a certain state due to an evidence, a new event or new something that occurs in the event space, and then our posterior belief, meaning what happens afterwards. What's my new belief? Given this evidence, what has it updated my understanding of how things are going at this point due to this new evidence? So this is a very important and powerful understanding that we should know, because it's also used in many machine learning models beyond naive Bayes. You may or may not have heard of like things like Bayesian neural networks, which also employ this Monte Carlo methods. They use this pretty extensively as well. So it is important to have a understanding of this to kind of go deeper in this stuff. So let's now tackle conditional probability. So if we look at the example on the right here, we have evidence that is the probability of a worker having a PhD. And we have a hypothesis that we have as well, that is that a worker is female given that they have a PhD. So what is conditional probability? So conditional probability is that the second event occurs given that the first event has already occurred. And this will build up into Bayes theorem in just a little bit. So just running through this example, we have the probability of a worker having a PhD, that being this full set of 15 people, right? Yeah, 15 workers who have a PhD. And then we have the probability that a worker is a female, which is this subset of 5 out of 30. So then now the given, the conditional probability is the probability that the first condition is true and the second condition is true, given over the second condition itself. And so we are calculating the probability of the second event occurring given that the first event has already occurred. Yeah. So now we can go a little bit into Bayes' theorem then. So then when we try and ask ourselves, what is the population of females given that they all have PhDs? So that will be the population of females times the population of PhD holders, given that we know that they are females, over the probability that someone is a female times the probability that you have a PhD given that you are a female, plus the probability you have a male that you are a male, times the probability that you have PhD given that you are male. And you can notice that this P of E is essentially all of the cases of this denominator is the total cases, the sum of total cases that sum up to the probability of the new evidence in itself. And so the theorem kind of works in this way. So we have the P of H times the P of E given H plus the probability of the other case. And this can extend on into 3 cases or 4 cases, etc., etc. And the top one is simply the intersection between the current hypothesis and the currently known conditional probability. As you can see here, this count is pretty clear. So we have 3 people who are both PhD holders and female over 3 PhD holders and 12 plus 12 male engineers, male PhD holders. Yeah. So if we look closely, we can see that this is the case. And this will feed into the next part. So these are the different components of the posterior probability that you may notice in notation, like if you do further reading on these aspects. So we have a posterior probability, we have a prior probability with the likelihood of the new evidence, and we have the predictor prior probability. Now this will go a little bit further. So we have another element, the chain rule of probability. So you might or might not remember from A levels, the incidence of 2 independent events, E and F. Basically, when you toss 2 different coins, the probability of both is 50%, 50%. Either way, you put it, and there's no actual intersection where the probability that you put heads on one affects the probability that you get heads on the other coin. And this can exist for infinite sequence of other events and chain on towards this, and calls back to our previous introduction of the sequence of events of do not like green eggs and ham, right? So then now we move towards naive Bayes itself. So this is simply taking that same idea of the Bayes theorem, and we are simply applying it multiple times on multiple tokens, as it will, independently. And so we see the prior probability is unchanged, but we have the likelihood of new evidence increased, and we have all the different cases all added up here at as the predictor prior probability. And then we can simplify this a little bit and take out the denominator. Now you can think about why this is the case for now. I think it'll be more clearer later on. But what are the 2 assumptions that we made over here? So the probability of the evidence is non-zero, and is constant through all the classes, such that the value of each class is equally affected. So it's cancelled out by the overall cases of P of E and the independence. So then now we can add on the naive Bayes aspect. So why is that simply? It's simply we take an argument max on the probability of the hypothesis. And this hypothesis can be a positive sentiment or a negative sentiment, or you get 3 classes, 4 classes, etc., etc. And we just add an argument max over this given equation. So don't be scared by this. This pi notation is simply just this time thing of E1 given H, etc., 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 etc. So what is the naive in naive Bayes? The naive aspect of the naive Bayes module is that the sequence of tokens does not actually matter. So Yoda might say, a cat am I, and I can say I'm a cat. And both are taken to mean the same thing, when in reality, it might not actually be the same idea or the same probabilities if we take it sequentially. And that's where the naive aspects of this naive Bayes algorithm comes about. Now, it'll be more easier to see this when we go through a worked example. So let's take a look at a tiny data set here. We have a naive Bayes example calculation here for you to just see and get the idea. So this data set looks a little bit like this. Y'all don't need to memorize it or anything. Just take a look. We have two classes and we have one prediction that we want to make, whether we are going to play tennis, given that the weather and the temperature is a certain way. So then we take this into a frequency table and we count for each case of whether it's sunny, overcast, or rainy, whether we play tennis, yes or no. And these are our P of PH and PH not. And so then we calculate this into a likelihood table by summing over the cases for yes and no, and having a fraction over it. And these act as our conditional probabilities. So we are assuming that yes, we went to play golf, that when it's sunny, yes, we went to play golf when it's overcast, and yes, we went to play golf when it's rainy. And we do this similarly for the temperature, whether it's hot, mild, or cool. And you can see the similar kind of calculation here. And we do this for every feature that we have in the data set. But notice there's a little bit of an issue here as well. But we'll work through that later. So then now we calculate the probability of yes given that this occurs, right? So whether the weather is overcast and the weather is cool, whether we play tennis. So now we just calculate by inversing that equation by applying the naive Bayes formula. So the probability of yes times the probability of outlook equals overcast, given that it's a yes, that yes, we went to play tennis, times the probability the temperature is cool, given that yes, we did play tennis. And we do the same for the no. And so we take the maximum of these two values. So the maximum of these two values is yes, we did went to go and play tennis, because we take the maximum of these two values, whether it's a yes or no. But notice we have this issue here, where whenever we have one instance where the weather is overcast, it's totally zero. So that's an issue that we want to resolve. So we'll need to go through some Laplace smoothing. And that might sound a little bit scary. What's Laplace smoothing? What's this formula? But actually it's quite manageable and quite easy once you break it down. So first we have the parameter that we want to smooth by. Y'all don't need to memorize this thing. Y'all will see, you'll be able to see the slides later. Let's just run through it. So first we have a parameter, right? We have a parameter that we indicate for how much we want to smooth. So in this case, that's 1. So we will smooth everything by 1, and we'll essentially add to each class. For each class, for each hypothesis, we'll add 1 to the value. So now we kind of resolve the issue of where whenever it's overcast, we'll get a probability of 0, which we wanted to resolve. Because there might be scenarios in the event space where it is overcast, but we still went to go play tennis in the case at all. And that is something that we need to account for. So we add 1 to the value. And so we also add so this domain of f, right? This domain of f, what does it simply mean? It simply means the different classes of f, of this f, meaning, like, for example, outlook. Is it overcast? Is it rainy? Or is it sunny? So we have 3. That's why we add 3 to each class. And we add 1 to each individual case itself. Yes. And so we add 1 to each class, and we add 3 to the total probability for that case. And that is for the parameter k equals 1. So if we add k equals 2, it'll similarly go where we'll have 2 here, we'll add 2 here. So the formula will be such that we add 6 into this into the denominator, where we'll have 18, and we'll add 2 here, where we'll have 6. So it becomes 1/3. And this smoothing allows us to then have proper cases where the probability is non-zero. So given that the outlook equals overcast and temperature is cool, we'll still play tennis, but at the very least, we ensure that we do not have a zero probability case. And there are scenarios where we can account for the outlook being overcast and not playing tennis. Yeah. So now let's see this in code. I'll pass the time now to Edmund.
All right, thank you, Stefan. Okay, can I share my screen? Thank you. All right, okay, thank you. Thanks everyone. Hope everyone's having a great time. So yes, kind of draggy so far, but then there's a lot of content to download today, but then I hope everyone's keeping up. There's a Slido in the chat. If anyone has any questions, can just feel free to ask away. Yeah, we answer them as to the best of our abilities. Yes, okay, so Stefan went through the naive Bayes walkthrough for the calculation. So in this context, we saw it as a rather relatable context of whether you want to play a certain sport during a certain weather conditions. So for now, we're going to segue into applying this concept into NLP. So may I want to ask, like, how does playing tennis relate to sentiment analysis? How does this relate to whether a piece of text predicts positive or negative sentiments? So in this way, you can think of it as playing tennis, yes or no. It can be translated into sentiments, negative or positive. And your outlook, sunny, rainy, overcast, can be thought of as, in a context of bag of words or convectorization, as whether the word exists inside the vocabulary of the particular sentence. So for example, if outlook equals, if you take the level as 2 levels, yes and no, for a particular word, then that will contribute to the naive Bayes calculation towards the end. So that's how we link this particular example to what our workshop is covering today, which is sentiment analysis using natural language processing. So I hope that's clearer for everyone. So with that, we can move on to a coding a walkthrough. I'll just show a simple implementation of the entire pipeline for naive Bayes in the context of sentiment analysis. All right, so okay, so now I'll be hopping over to the Colab. So in the Colab, you can see that there's a bunch of modules that we have imported. So I'll be going through them, not say individually, but as a section. So previously, Javier has nicely went through a few of the packages and their use cases. And then so especially NLTK, but then now we're going to explore outside of NLTK a bit, and also the different methods, because I think there was one of the questions inside the Q&A that asked split or NLTK tokenize. I mean, they all achieve the same end purpose, so it's up to you which you prefer to use. They have all similar use cases. So yeah, in this case, it's quite flexible. So there's no right answer, but then just as long as the function meets your use case. Okay, so now we're going into importing our modules. So sklearn is a module that is heavily used in machine learning. So in sklearn, we have a lot of supervised and unsupervised learning modules. And in today's context, we're going to look into naive Bayes model, in particular multinomial naive Bayes, because we're looking at multiple vocabulary, and we're looking at, in this case, like multiple variables inside our model. Okay, then we have our matrix. So when we build our model, we would like to also evaluate the effectiveness of this model. We would like to, the performance, whether this model is good in real life or not, whether you want to roll it out into productionization. So these are some scores that you want to look at. Then also there's like label encoding, which will encode your positives and negatives into ones and zeros, which are machine readable. Then of course there's the train test split, which allows you to train your model and also evaluate it on test data. Then also we have our vectorization methods from sklearn. So just now we talked about TF-IDF and count vectorization. So this is it appearing again. Yep. So then we have our NLP modules, NLTK, so stop word, stemming, and lementization, which was covered earlier. Then of course we have our generic modules that help us achieve certain segue functions, pandas, data frame, numpy into like data array types, date times into timing, regex into our text processing, and of course counter, which will allow us to count factors. All right, so moving on, we like to load in the data. So previously, Javier has showed us how to load the data, the IMDb sentiment analysis into this notebook. So this is it here. It's the same notebook. So we assume that's already been imported. And then we take a preview of it. So there's these reviews and these sentiments. But you might, from a get-go, you might notice it's quite, say, unprocessed. It's quite raw because these data that's presumably directly scraped from the IMDb website still contains the HTML text, and then it contains some stop words like I, this, that may not contribute to this overall sentiment. So we have to remove them basically. Okay, so before that, just like quick sneak peek and preview of the count of negative and positives in these in this book, in this corpus of documents, in other words, collection of sentences. So we can see here it's a nicely balanced data set. It's 25,000 negative comments and 25,000 positive comments. So very nice. We can, this will affect the choice of a matrix we use later to evaluate the model. All right, so I'll talk more about that later. So we just jump straight into text pre-processing. So just now, Javier mentioned about lementizing, stemming, stop words. So yeah, in this short function here, we would like to, it achieves all that function. So you can see here that this is a regex expression to remove URLs and filter for alphanumeric characters only. So don't worry about regex. It looks very scary. I myself, I don't even really understand the whole of regex, but then there are regex translators online that you can Google, and you can really figure out through those websites what's the regex expression for your particular use case. So that's that. So we want to process our text. So in this particular function, we will first replace URLs and non-alphanumeric characters with a blank space. And then we like to turn into a lowercase, and we like to remove trailing white spaces. So that's done within this one line. So one line of code in Python is able to really achieve so many things. So like regex expression, lowercase, and remove trailing spaces. So then we create an empty array for an empty list so that we can store our stemmed and lementized words. So first we split the words. So just now split was asked inside the Q&A. So yes, split can be used also. So it's used in this case. So our text sentences will be, well, our sentences will be split into individual word tokens. And then these tokens will be checked against the list of stop words. So we can preview the stop words if you want. So stop words. Hopefully, yeah. So these are the stop words. Yeah. So you just check against this set of stop words, and also or lementize and stem them. Yeah. So you can either use both or use one of them. But I want to really reduce it even to its lowest form. So I perform both. Yes. So then after that we return it in a string format again after that. So you can see that after cleaning, we have removed our HTML text and we have removed some stop words so that this is the clean sentences. All right, so after cleaning the text through this processing function, we can proceed to really build our model. So when we want to build our model, what's needed? We need raw data. We need data in the form of machine readable text. Okay, raw words cannot be read by a machine. The words need to be transformed into numbers. Excuse me. The words need to transform into numbers. So these numbers are in a sense that like ones and zeros, or a matrix representation of the particular word. So the first thing we do is, before that actually, is to split it into train and test data. So assume, for those who are unfamiliar with this concept of train test split, basically we are trying to train our model on a fraction of the data available. So in this case, we are doing 80% into train, 20% into test, so that after training the model on 80% of the data, we can evaluate the model on the 20% of data that is not seen by the model. So this is important because we do not want like unseen data to influence the training of the model, so that there's no model leakage, no data leakage rather. Yeah. So in this case, you can see that our model will be trained on 40,000 reviews, and 10,000 reviews will be used to test the model's effectiveness. So this is done here. And then we have label encoding. So as we saw in the preview, sentiment was positive or negative. A machine doesn't know what positive or negative is. So this label encoding transforms positive, negative into 1 and 0. So 1 refers to positive, 0 refers to negative. So that in training with the data, the machine can understand what it's doing. So yes, so this particular cell does that. So do not be too afraid of all this fitting. This is just how the label encoder function works. So the interesting thing about this is that this label encoder function, it works for even more than 2 factors if there are. So in this case, there is positive, negative, but in future, if you encounter another data set, let's say your Iris data set or whatever other data sets where your predicted class may have more than 2, label encoder is able to capture all different predictions and transform them into numbers. So maybe 0, 1, 2, 3 up to. It depends on the number of classes there are. All right, so that's our Y train and Y test. So Y train is the labels for training set. Y test is the labels for test set. All right. Okay, so up to here, and if there are any questions, y'all can just throw into the Slido. I think our friendly SDS members will also help to answer them. I can answer them later too. All right. So next, after we create our Y and our labels, we will proceed to vectorize our text. So vectorizing, as mentioned earlier, is to transform our language text, our natural raw text, into machine readable vector representations. So back of words is first, so which is, in other words, count vectorization. So we initialize a count vectorizer, and this count vectorizer is from sklearn. So this is initializing an instance of the model. And after, what you can do is we can fit and transform it on the training data. So what it's doing here is that it's fitting. So this building the vocabulary. So essentially what it's doing here is that it's creating an entire array of unique words, and then this will form the basis of the model later. So as you can see in this what do you call this data frame over here, there's 63,106 rows, which represents 63,106 unique words inside the training data. So yes, so there's many words, and these numbers here, don't worry about them. There's IDs, there is text ID. So this one you can safely ignore. But this is the important thing to understand, that this fitting is creating vocabulary. Then after that, we're transforming each individual row into a vector. So how this vector will look like is essentially every text word will take up an index space, and then if that particular word appears in that sentence, that respective index will take a value of 1, if not 0. So just let me annotate real quick as a quick example. So for example, let's just say a simple vocab, we have say, okay, I'm just going to take the cat. Oh my gosh. Okay, cat, ask, and fight. Okay. So is essentially what it's doing here, sorry for my handwriting, is that, okay, so just keep track that cat is index position 0, ask is index position 1, fight is 2. So for example, a sentence is ask cat. Okay, so after going through this count vectorization, the vector representation will be 1, 1, 0. Yeah, so essentially it compares it against the entire vocab and creates a sparse matrix of whatever vocab is in that particular sentence. So yeah, so that's what it's doing here. So I'll clear my drawings. Yes. Okay, so yeah, hope that's clear for everyone. And then for TF-IDF vectorization, okay, sorry, before that, what I'm doing here is I'm clearing, importing a garbage collector and clearing the memory because Colab has like limited memory resources, so I don't want to crash it. So before we work with like even more sparse matrices, I like to clear the memory so that it doesn't crash. So over here, we clear memory. Then here we initialize our TF-IDF vectorizer, and then we similarly vectorize our vocabulary. We vectorize our text. Yep, our training text. Then after that, this will give follow that what do you call this? This formula over here, and then we'll assign every sentence, every sentence with an array of TF-IDF values to them. So yeah, do not worry if you don't really understand this one at the moment because this is quite an abstract number. So for now, you just take it at face value that the values assigned to each word is its relative importance inside the array. So instead of ones and zeros, it might be even a fraction or it might be decimals. Yeah, to represent importance. So after working with sparse matrix, I will again clear the memory. All right, so that's us vectorizing our text. So I hope that everyone's following at the moment. If anyone has more questions, you can just ask on the side. Yes, okay. So after we vectorize our text, what we're going to do next is we're going to build the model based on our text vectors. So over here, what we're doing is we're building a pipeline of that's able to take in training and testing data and output the model performance in one flow. So this is this might seem at the moment slightly complicated, but don't worry, I'll explain line by line and then we'll hopefully have a better understanding of it. All right, so what I'm doing here is that these are the training data that we're going to work with. So the first one is the training data that's been count vectorized, and then along with the training data that has been TF-IDF vectorized, similar for testing array. So these are the inputs into our model and our testing inputs for our model respectively. All right, and then this is a result store. It's just a mega dictionary that we'll use to store all relevant information, and then we'll transform it into a nice readable pandas data frame, which can be exported into CSV if you'd like to, so that the results are presentable to people. And then we have our names of the respective names of the model we're using. So this is will help us to label later on. All right, so I assume that everyone here knows what functions are, so I'll just quickly move into it. So here what it does is it just returns, get result store returns this particular result store in a nice data frame format that is very readable. And then I won't go too much into F1 scores and all these other scores today because as what I mentioned earlier, the data set is very balanced. It's about 50-50. So for today, accuracy works fine. So this is the only metric that everyone needs to look out for today. But for enrichment, if anyone else wants to further their learning, you can look into other matrices such as precision recall, AUC, and F1 score, because as your data becomes imbalanced, these other matrices play more important roles in evaluating performances. Yeah, so today, just look at accuracy. All right, so next we have another function called, okay, before that, this function, what it does is that given predictions, it returns the value of the matrix, sorry, the matrix, yeah. All right, so then we have our main, what do you call this? A main function that initializes our pipeline. Okay, so what it takes in a model. So the model in this case is our multinomial naive Bayes model that we're going to initialize in the next cell. So in general, because a lot of the models are under sklearn, so that they have very similar syntax. So this particular function can actually be generalized to many sklearn models out there. So it doesn't need to be a multinomial naive Bayes. You can do stuff like maybe random forests or etc. And then just pass that model into this result. This function, you should be able to get a result. Yeah. So and then once we pass in the model, which in this case is multinomial naive Bayes, we'll iterate through the training data arrays. So what it does here is that it iterates through the arrays specified by this. So another good thing about this function is that it's scalable upwards. So this why I really like this function, that if you have other training data that follows a different kind of vectorization, you can just add it to this array. Say, for example, if you have a word to bag, you have a bird, glove, whatever, different kinds of matrix representation of your text, you can just add it to this array. And then this particular function will similarly iterate through all of them. So this is really a one-stop shop pipeline that can evaluate lots of things. Yeah, so what it does here is just for each of the arrays, it assigns the specific training and testing data into this specific iteration. So this is what it's doing here. Then what it's doing here is just simply having a string representation of the name of the model that is currently doing. So for example, you can see here that the name MND count, because there's model name, which is multinomial naive Bayes MND, which we passed in here, and count string name I, which came from here, this array here. So is that, sorry, this array here, so that in our pandas data frame later, we can identify easily which row it represents what model and what vectorization method. All right, so moving that, I like to explain why we're using time here. So because multinomial naive Bayes is actually a very, very fast training model as compared to, say, deep learning models like LSTM and all of that. So this here can show the timing it takes to actually train the model. So perhaps in the Wednesday's class, if you like to compare the timing of training, you can easily do that. So in some use cases, time is of the essence, and you have very limited time to train models that need to be rolled out into productionization. So as you scale up to bigger data sets, the time will increase exponentially. So time is quite important here. So this is where we decide what model we might want to use next time. So MND is quite fast. It only takes 0.04 seconds. So it's almost instantaneous. Yep. So what it's doing here is that between the time logging is actually fitting the model. So fitting the model means training the model. So what it's doing is that it's passing the specified X-train array and the Y-train revel. Okay, revel here means we're unpacking the labels, because label encoder outputs an array of arrays. So what is this just? It's just unnesting them and creating one singular array of the same level of labels. So that is fitted with the X-train iteration. And then you're fitting it to the MND model. So you're training the model. So now the model is trained. And then after the model is trained, it can be used to predict. All right, so after that, we jump straight into prediction. So we train on the train set and we predict on the test set. So in this concept is that because we want a very accurate and reliable result that can be used for real life. So when we predict it on unseen data, just like in real life. So this is how we evaluate our models. So you can see here that there are two different kinds of predictions. One of them is predicting probabilities, and one of them is predicting binary. So why you want to predict probabilities? Because some of our matrix requires probabilities instead of binaries. Say, for example, your AUC, which is area under the curve of the ROC curve. This one you don't need to worry about it today, but then just know that prediction probabilities are sometimes used for matrix. So this can be used for next time if you want to explore deeper. But for today, I think everyone will be more interested in prediction binary, which predicts ones or zeros. So in this case, that when you put in a piece of text, it predicts one, either 1 or 0, 1 meaning positive sentiment or 0 meaning negative sentiment. So this is what it does, and then it stores it in an array also. So this is an array of predictions. And after that, we pass in the predictions and prediction probability into this calculate results function, which is this one. It returns us a very nice dictionary of all the matrix of our concern. So in this case, it's all these, and then it stores into this variable here. Then we can further expand this dictionary by including the time taken, which is the duration, which is calculated here in seconds. Then also we can store the model so that we can use this model for predicting, for productionization, for predicting future inputs. And we get just for the name for the sake of identification in our pandas data frame. Yep. So that returns the results. So I just run this again. Hopefully it didn't crash. Okay, good. So what you can see here is that it produces a pretty nice readable table that can be nicely exported to a CSV. So you might be asking, what is this and multinomial NB here, multinomial NB here? This is the model object, the trained model object, which is stored in the dictionary. But then when it's represented in text, in string format, it's just the name of its object class, which is multinomial NP. So this one, I will show you what's the use of it later, but just in case some of you may be wondering. So yeah, then this is the identifier of what vectorizer we're using. All right, so now that we have created our model, we have some results of the model. So you can see here that MNB using count vectorization has what we're looking at, accuracy of about 85%. And then TF-IDF factorization using multinomial base has 86% accuracy. So that out of the 10,000 out of the 10,000 testing data that we fed into the model, 86% is and 85% respectively of them are predicted correctly. So that's a pretty good score for a model that only takes super short time to train. So yeah, this serves as actually a very good baseline model for comparing, for executing NLP related tasks. So multinomial naive Bayes is usually the first step before we use more complex models such as deep learning models. And then this serves as a baseline for us to really create models that outperform this. So this is usually used as a get-go, yeah, as a starting point. All right, so you can see here that precision accuracy is higher for TF-IDF. So meaning that you can say here that this slight difference in accuracy can be attributed because of the relative importance of each word. So perhaps that it's not enough for the presence of the word, but the word in comparison to the presence of the word in comparison to the rest of the documents also play a very important role. Say for instance that rarer words such as, okay, if you look at if we look at this, rarer words such as cool, I don't think anyone spells cool with this many zeros, but this is probably a very rare spelling of this word. So this word is rare, so it's placed as a more important word in TF-IDF in context. So usually if the model finds the word cool in the vocabulary, it attributes it to a higher weight. So it will, I assume it's a positive sentiment, it will, to a high probability, classify it as positive. So perhaps there's a lot of slang going on in IMDb review website. Not a lot of them use proper English. That's just an assumption for now. I don't have perfect data. I haven't really processed to that level of granularity. So that's just an assumption for now. Perhaps some of the rarer words have higher weightage. So that results in higher accuracy score for TAF IDF because the model is trained better. It's a stronger, better performing model. So yeah, so that is the basic pipeline of generating a trained multinomial naive Bayes model, and also storing them in a easily accessible dictionary format. So yeah, so now let's predict new inputs. So assume that now you want to productionize our model. What you can do is that let's just go through this really simple review here. So this movie is interesting. I really enjoy it. Or this movie was so boring. How could anyone sit through without falling asleep? So to us humans, intuitively, we can tell that this is a positive sentiment and that this is a negative sentiment. But then to a machine, it's not as straightforward. So it needs to go through the entire process of pre-processing, vectorizing, and then finally feeding into the naive Bayes model or whatever model you choose. Okay, so let's just show an example here. So let's say I want to first predict the input of this first input text. So I assign it to input text. And then first we need to pre-process our input text. So pre-process was the function we defined earlier that removes all stop words, that stems, lementizes, and also filters it through that regular expression. So let's pre-process it and preview our process text. So movie interest, really enjoy. So might seem gibberish to us humans, but the machine finds this more understandable. Counterintuitively, this is so. So after that, we can vectorize it. So what I do is we take both the TF-IDF vectorizer and count vectorize, and then we transform them individually. So this is the process text, which is this thing. So you just pass it in. And why is in a list? Because a transform takes in a list of sentences. So it has to be in this particular format, an iterable array or some sort. So this is how it passes in. And then after that, we extract the MNB model, the multinomial naive Bayes model, from our dictionary just now. So we had a dictionary here. This is where we extract a model we want to use for productionization. So here we extract it out. So we have one that is TF-IDF that's trained on TF-IDF, and we have one that's trained on the count vectorized. So now over here we have two trained models, and we can use either one of them for prediction. So let's predict. Okay, so I haven't run this yet. So this pre-process that vectorizes the text, and what this does is that it takes out the model. Okay, so now we have the trained models that we can use for prediction. So now we predict. Oh, predict one. One means positive. So as you can see here, the model has successfully predicted that the input text one is of positive sentiment. So let's try the count vectorization one. Also one. So you can see here that the machine has, yes, successfully done it. So let's try it with the other one. The movie was so boring. So let's change and rerun the processing. So movie bore, whatever. Then we vectorize it. Yeah, it's already been taken out. Let's take it out again. And then we predict, it's predict 0. So you can see here that, very nice. It successfully predicted the classes. Yeah, so this model is, you can say that it's pretty interesting, it's pretty well trained. So that's nice. Okay, so yeah, at this point of time, it's been quite a lot of content download so far, sorry. Yeah, if anyone have any questions at the moment, feel free to really ask in the chat. Sorry, not in the chat, in the Slido. Okay, so this, sorry, so we can just open this up. Any questions? Okay. All right, so yes, so nicely the questions has been asked and answered already. So maybe let's go through again. So let me see. All right, so specific to what I've just gone through, train test set of tokens like that, or by order. So train test split by default is okay, I'll assume that whether this person is asking whether test set and train set are split randomly. Yes, the answer is yes, they're split randomly. So let's go back to my train test split. So by default it's split randomly. But then what I did was I used the random state equals 42. So this random split will be reproducible. So every time you run this Turing test split, although the split is random, since we specified the random state, the random allocation will always be the same every time you run it. So it's reproducible. So if you remove this random state or you specify another value, when you run it multiple times, each time produces a different split. So yeah, I hope that answers the question. So yeah. So yeah, are there any other questions? Okay, I hope there are no other questions. Okay, I'll just pause for maybe 1 minute and see if anyone has any questions, just feel free to ask. All right, so
I think there's a question in the Slido.
okay.
Above.
Above.
How are the models built?
Exactly how the models built. Okay, so for this one, we want to employ some wishful thinking. Going into exactly how the models are built is too advanced. So just assume that when we execute our model.fit, the model is able to create is able to train based on the training data. So in this case, you have a naive Bayes model. So okay, let me. So it really creates this. So in this particular instance of the naive Bayes model, after you train it, it creates a sort of a distribution, and then in the probability distribution, right? As you pass in the vocabulary, it forms this. It goes according to the distribution, and then also this particular formula. So like say instead of outlook equals overcast, temperature equals cool, we're looking at a whole array of vocabulary. So there might be in this just now's case there was 63,000 words. So in this case there'll be 63,000 columns, each representing one word, and its associated factor value is either 1 or 0. So after that, it will be passed into this particular formula. Then we will be really generating this particular values. So in this case of yes or no, or positive or negative, it is the argmax of this two. So of course we are not. I don't want to write out 63,000 terms in the equation. That's take too much time. So just assume that the machine is able to do it efficiently, and that is able to produce these individual probabilities and multiply them together. Yeah, I hope that answers the question for this particular context. Okay, let's refresh the Slido. Any other questions? Yes, later they'll be sent, no worries. Yeah, so Stefan will be sending them later. Yep. If any other questions? Okay, so I currently.
Okay, actually, there's one thing that I do want to go through. Edwin, you can go back to the slide. I think that very slide that you were at about the Laplace.
Oh yes, this one. Okay.
Yeah. So regarding the reason why we need the Laplace, right? So imagine we have like the Imdb data set, right? So we have like a lot of different words and we have a lot of different counts and whatnot, right? But in the actual like sentence that we're gonna like predict or whatever, right? We will not really have 6,400 different words, right? So each one of the words can occur like I have a cat or whatever, right? So because we have like a very sparse data set, right? So the number of like possible words that we have in the naive Bayes model is up to like X number. And so that's why it's important to do the Laplace smoothing so that we don't encounter this zero problem, which would be very evident or very if we didn't do the Laplace smoothing, it would almost every single time we would have the issue of like we have the issue of where we'll get a zero value quite often, because sometimes you use like different words that are not encountered in the data set. So minimally they'll have like a probability of 1 on each. So that means that it's a probability of 0.5, or whether it's a positive or negative sentiment, or like if you have more classes, it'll be distributed. And so if you study information theory or whatever, this would lead to no change in entropy or information gain based on that. And that's why we need to, that's why we generally do like a Laplace smoothing of k equals 1 as well. Yeah.
Thanks for the
After that,
explanation.
if you're, I have a bunch of links for you all here. We really greatly appreciate if you could leave your valued feedback for us here. And of course, we also send this along with the recording for this workshop, following up from this later down the line. Yeah. So now, do you have